on because this is the part that matters.
Raise the gate.
Just this one?
Yeah, I know. The other one I didn't.
All right, anyone else need this? All right, let me start by saying this. Do I care if you could do all of these and that they made sense and then you did them all flawlessly? No, that's not the point of physics. That's not the point of practice. You practice to figure out what you don't know, so we can practice that together and then theoretically improve it, right? My hope was that you could at least read these, set them up, draw free body diagrams, and just start to think about them. But so far today, we've worked like number 5, we worked number 10, 11, 13, 15. We can do 2 or 3, totally your choice. Which ones are we thinking, if any? I got a request for 16. We'll start with that first. So 16, and here's what I'll do. I'll just kind of snip these. Oh, I actually had that one already snipped over here. So to do 16, we have to do 15, but we'll kind of just jump straight to 16, assuming we lay some foundational work here. So 16 asks us to repeat 15, which is complicated, with friction. So you're taking a hard problem and make it even harder. It'll be a little rough, but we'll do it. Okay, friction. No, never mind. It's been a long few days with no students. So thank you. Pity laughter. I'll accept it. If we have multiple objects, how many free body diagrams do we need? Multiple. In this case, 2. So if I draw a free body diagram here, what forces would be acting on this 3 kilogram block?
Normal.
Okay.
Straight up.
Gravity.
Straight down.
No, gravitational force.
I forgot everything. My 3 days.
You're the one who hasn't been here for 3 days.
Okay.
Ooh.
FG straight down and
Supposed to be friction.
okay, so if we are jumping straight to number 16, which we can do, there would be a frictional force backwards, and then a tension to the right. Right, if we call this rope here a tension. Okay, what about on object 2? Same, right? FG. Then do the tension with a given value of 20 newtons, and we have this tension as well. Multiple tensions. Deal. So thinking about the forces, I'm sorry. If we want to find, in the first part, the acceleration of my blocks, multiple, then I have to think about the whole system, right? The total mass. Because when I pull on my little 2 over here, I'm not just moving the 2. What all am I moving? The 3 as well. So a total of 5. Okay, the other block is moving even though the force is not being applied to it. This is the same idea that if I kick a ball or something, and there's like another ball attached to it or something, even though I didn't kick that ball, it's moving. So you have to think about the whole thing, the whole system. Okay, our definition of system is going to become really important soon. So think about that. I would have a net force equal to the tension. I'm going to call this like tension A. Tension A. What is opposing that tension?
For which activity?
We're focusing on this.
The other tension.
So the other tension, so minus tension B. And we actually forgot something on our free bonds.
Friction.
Friction. So minus tension, minus the friction on object B. Now, this tension is to the right. So what do I have to do with it? If I'm thinking about my whole system. So like I've got all of my forces here now. Now I'm shifting my look over here. So I would actually, then this is tension B. I would have plus tension B, plus tension B, minus friction force on block A. Again, just referring to this is A. This is B. So that looks like a lot, and that's equal to the mass total times the acceleration. Now, does anything go away?
Yeah.
Yes.
Tension B.
Tension B actually goes away because if I'm looking at the whole system, I don't care what the tension is between the ropes. That has no bearing on how my blocks accelerate. Okay, so that's good. That's helpful. What else?
Nothing.
Nothing else. So let's rewrite. Tension A minus. What do I remember about force of friction?
Coefficient.
It's the coefficient of friction times
the normal.
normal force. Good. And in the case of our normal forces, if we look in our y direction, up and down, is there anything else besides normal force in that G? No. So therefore, this mu Fn is actually just equal to mu Fg. Because in the y direction, normal force and Fg are the only two forces that are equal. If I pull on a block horizontally, here, is it going to fly up in the air?
No.
No. So I can assume that these two things are equal to each other. So I could rewrite this as tension A minus mu times Fg B minus, same thing with the force of friction for A, mu Fga, exactly. Because there's no vertical forces besides for Fg and Fn. Equals mass total times acceleration. And so here, tension on A, which is 20 newtons, minus mu, they gave me was 0.21 times FGB plus U, which is 20 newtons, plus U again, 2 times 10, by the way, and times G. I just did Fg, instead of writing 2 times 10 meters per second squared, I just went ahead and wrote 20. Minus 0.21 times Fga, which would be 30, equals, what's my total mass? 5 newtons, so 3 plus 2, right? 5, you can figure out either one. But I'm explicitly writing like this just to show that I'm thinking about both blocks, times the whole acceleration. A bunch of numbers. 20 minus a number, divided by a number. Total, we get 1.9 meters per second squared. Now, compared to in 15, if you solved it, 15's acceleration was 4 meters per second squared. Why is this lower?
Because it has friction.
It has friction. It's that easy. When you add friction, you're going to reduce the acceleration. It's going to generate heat, sound, all kinds of things. And then the last part is, what is the tension of the string? The tension went away when we considered the system. So how can I find the tension? It's not zero. If I was to pull two objects together, I don't really know if I can do this, but I can try. Let's say I have like a book tied to another book like this, but I'm applying a force to this book. There would be a tension in between these books in this rope. But how do I find it? You have to pick a block. So if we choose one of the blocks, for example, if I just choose, I think let's choose this one. That looks a little easier. All I have is tension and net force of friction. So net force just on block A would be the tension B minus force of friction A equals mass times acceleration. And this is, again, just for block A. Because now, instead of this tension over here, tension A that I was applying, the 20 newtons, I'm solving for this tension. So it'd be the force of friction on block A plus mass times acceleration of block A. This means I would do mu Fg A plus mass of A times acceleration. So 0.21 times 30 plus 3 times, what acceleration goes here? Is that 9.8 meters squared or something? No, that is the acceleration of my system, 1.9 meters per second squared. So 0.21 times 30 plus 3 times 1.9 value that I found gives me a tension of 12 newtons for part B. Now, if we want to stop and check ourselves, how do I know that's right? Where? I mean, we could go back and plug it in here. We would have a -12 and a +12. So I mean, technically it's canceled, but
How did we get the 20 Newton friction
which one?
on B,
For B here?
on A? Like, how do we get 20 Newton friction?
This?
Yeah.
This is the applied tension.
Okay.
Oh, Fg, this is mass times gravity. So mass of block V times 10. Yeah, mass of V times gravity. That would be 2 times 10.
What is this test?
That's
No, I mean, like, what's the tension that we get? Like, how did we get TA?
TA was given. That was the applied force here.
Oh, okay.
Now, and that's what we have to look at, see if it's gotten to the point. How do I know this is right? Because it's less than 20. If I would have gotten greater than 20, meaning that the tension between the ropes is greater than the tension here that I'm applying, something is wrong. Because if my tension is more on this left side than the right side, then how would the system have to accelerate? Go back to the very beginning of our notes on net force. We did winners minus losers, right? If at the end of the problem we get a bigger number on the other side than where we expected, then the one that we pick as the winner is actually the loser. So that would mean that the system's moving left instead of right. This is a lot. A lot. What are we thinking? How are we feeling?
Yes.
Let's do a different one, maybe. Any others you want to look at? The very first one, like number 1?
Yeah.
You can do that. Yeah, one's a throwback, because what do we have to do on it? We'll do one and then we'll take a short break, y'all, I promise. We're almost there. Yeah, it's kinematics. We gotta throw it down.
All this was really confusing.
That's why we practice.
Well, I just might have to learn everything. I don't know.
I think
Last week was a hard focusing.
that's the point of school, right?
Yeah.
Yeah, I realized last week was a wash with the
I
election.
don't know. I could not focus last week on anything. Actually, the past like 2 weeks, but this week my tension is for some reason here. So.
Well, we're in now.
Oh
so-
yeah.
How much force, and this is actually a good segue because we're going to do the catch a bullet thing in a minute. How much force do the expanding gases in a gun barrel exert on a 6-gram bullet as it accelerates from rest to 500 meters per second in a 0.7 meter long barrel? So, for example, if we know the length of our barrel of our weapon, like this, for example, 0.7 meters, I will in a minute or Nate, I mean, whoever volunteers. And if I have a 6-gram bullet inside, and I know the final speed at the tip of the thing, and it started at 0, obviously, then I have to use kinematics. So if we do that, what do I have to do with this?
Yes.
We got to convert it, right? That is equal to 0.006 kgs. That's step 1. Because kilogram, 1,000, right? Okay, got it. So thinking about that, my final speed at the end of the barrel is equal to the original speed plus 2 times acceleration, x minus x sub 1. Third kinematic formula, because I know nothing about time. You don't know time? This is your friend. Into the barrel, it's going 500. So 500 meters per second equals 0 plus 2 times the acceleration, which we don't know, times the length of the barrel, 0.7 meters. Or if you wanted to do 0.7 meters minus it started at 0 meters at the end of the gun, whatever, it doesn't matter. Therefore, giving you an acceleration in the gun of a big number, 1.8 times 10 to the 5th meters per second squared. Because gunpowder go boom. And
How do you put it in that
fast.
form? I honestly don't know. I always try out the whole number.
Right, I can show that. So 500 squared. Let me get my calculator.
Was this like a long time ago?
Yeah, this is a thing we can talk about. 500 squared is 250,000 divided by 2 times 0.7, all in parentheses because, please excuse my dear Aunt Sally, gives you this number, 178,571.43. And the unit is meters per second squared. Is this a valid answer? Yes, absolutely. But because most people are not going to like it if you say that, you can convert it to scientific notation. Scientific notation basically is this, where you want your number to be between 1 and 10. So I have to move my decimal place however many times to get it there. So the short story is, if I go here from where it is currently, 1, 2, 3, 4, 5, I would really have 1.78 times 10 to the 5th, because I moved the decimal place 5 times, meters per second squared. But in the problem, the reason why I rounded it up to 1.8, I have 2 significant figures here, 6.0. I have, gosh, I can never remember the 0.01s. I think that's 3. But, and then this one has 2 as well. So really my final answer should have like 2 significant figures. So that's why I rounded it up to 1.8. But if you put this on a test, you'd get it right as well.
Yeah, no, we definitely did scientific notation last year, but it was never explained to us like why it was called out or something.
So that's the reason. And if you had a really, really tiny number, like 0.000000000 Q9, sorry, that's another 0. I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'd be 9.0 times 10 to the negative 9th, which is nano.
Oh,
And same thing, just because I moved it 9 places.
wow. Learning something. Why did they do 9.0 and not just 9?
It's just the notation. Because typically it would be like
Could you just say 9 to the 10 negative 9? Or you want to say
9 times 10 to the negative 9. You
Yeah.
could, but just saying 9.0 is just more specific.
On your calculator, what's the difference in pushing the times 10 to the and the e button?
Great question. It's the same thing. If I entered this in the calculator, it would say 1.78 E5. Yep. So like, yeah. Good questions.
That's good to know.
Good questions. Andrew.
Say how much force.
Yeah, so this is, we're not done. Yeah. So this is the acceleration. So how do I get the force, Andrew? Finish this out.
You do have people.
Yeah, F equals ma. So we have the mass, 0.006, times the acceleration, 1.78, times 10 to the 5th, meters per second squared. Sorry, I was having a math moment, which gives me F net, which is a small number times a big number. Still going to give me a pretty big number. I mean, you're getting shot, and it's 1,080 newtons.
Oh.
It's enough to hurt, for sure.
This is a physics question, but it's off topic from this. Do you have any advice on how to be better on the reading quizzes? Because I read them every time, and then I get 75 every time.
Do you quiz yourself? Do
I
you
do
like
the little
the
questions.
stop and think?
Olivia, don't read it at all, just do the bottom. You're good.
No, John, do not.
Citizen-
I would read it, put it in your own words, check yourself, do the questions, and then, I don't know, just read the questions carefully.
Don't read all of it. Just remember the answer.
John, that's the worst option.
I do that.
I got a $112 because I did that.
No, it's because you actually know this stuff, John. It's because you took actual.
Yeah, you had honors as the upper hand. All right, let's do this. Before we go further, let's take a short brain break. We can brain break to refocus. That's what I would recommend. Most people just don't read like keywords and then miss it because they. This is a COVID-friendly one. Harley, will you assist me for a moment?
Yes.
Okay. This is called the 3-1-2. Let me turn so y'all can see a little better. So Harley, come face me here. You're going to this with your feet. You're gonna click your my right foot. You're gonna hit your right foot. So 1, 2, 3. So ready? 1, 2, 3. And then we're gonna flip to the left and do 1, and then go back to the right and do 2. 1, 2. And then we flip. So now left 3. 1, 2, 3. 1. And then 1, 2. So 3, 1, 2, 3, 1, 2, 3, 1, 2. Makes sense? Give it a shot. Stand up and give it a shot. People at home, you can do it with your wall, or you get out your good old Guns N' Roses, do the 2-finger gun maybe. Oh gosh.
So we're going.
You can start with single gun, and then when you get good at that, you can go for 2-finger gun.
1, 2,
Watch out, on the move. This is your brain break. You got to get up and try it, y'all. Stand up, stand up. This is brain science to reconnect your left and right hemispheres of
Everybody get at it.
30 seconds. 3, 1, 2.
We're so good.
Good job,
Let's go.
All right, Peach, good stuff. Good stuff. All right. So let's discard our ink here.
1, 2.
1, 2, 3, 1, 2. 3, 1, 3.
And a 1, and a 2, and a... All right, dance auditions will be tomorrow.
Oh my gosh, I'm fine.
What else do we need to look at? We have time for like one more probably, and then we can do the gun thing real quick. Harley, 5?
The 3 part.
Yeah. I'm glad you asked this one because we didn't do this in third period, and I think they're going to regret it one day. And then look back on their lives. So, number 5. What's
It's a little specific.
The normal force is not very
normal force? Okay, well, let's draw our question. I think that'll help. Here's our lawnmower. Nice Husqvarna. And if we think about how we usually push a lawnmower, most of us do not get down behind the lawnmower like this and like push it. Typically you stand and you apply a force down the bars, which means in reality, you're at an angle. And so they tell us that angle here is 30 degrees. And that 90 Newton force is partially forward and also partially downwards because it looks like we're mowing over somebody. In reality, we have to not only push the thing forward, but we also have to hold it down because think about the waves are spinning and there's a lot of maybe air being pushed down. I don't know. But the point is, it's a simple machine. So it allows us to do less work but still propel the mower forward. So we have to think about not the applied force down the pipe, but the applied force in the X direction and the applied force in the Y direction. So on a 3-body diagram, we would have force applied X, FG, and force applied Y. Because part of me pushing down on the handle as I'm walking forward at a 30-degree angle is going into the ground. What's opposing those forces?
Is it natural force?
Normal force. It's okay. And backwards, we would have friction. And what do we know about force applied X and friction?
I don't know.
What do we know about the whole problem? The key word.
Constant speed.
Constant speed. What's that mean, Andrew? Equilibrium. This is called dynamic equilibrium. And so if we're in dynamic equilibrium, that means the net force, which would be force applied X minus force of friction equals ma. But if I'm moving at constant speed, what's my acceleration? 0, which means this goes away, which means force applied X equals force of friction. Which means if I want to know what's the frictional force, all I have to do is FAX. How do I find FA sub X? I've got an angle, I've got a force. SOHCAHTOA time. So which one?
I thought it was on.
What's the SOHCAHTOA time song?
Hold on, so it's the triangle, and so here's the angle,
Here's my force.
and we wanna go this way, so, I don't know.
Here's our triangle that she just drew with her arms in the air. I'm here, 30 degrees, 30 inches, 30 degrees. I want FA sub X, which is adjacent or opposite? That's adjacent, right? From this, it's up right next to it. The opposite would be over here. So I want cosine. Thank you, Doctor. So force applied times the cosine of the angle, 30, would be the force friction. They gave me the force applied. It's 90 newtons. 90 newtons, cosine of 30, force friction. This means force friction is equal to 78.
At some point, can we do a little lesson over SOHCAHTOA?
We can.
Because some of us never learned it in geometry, and some of
Yes.
us don't have to do it now.
Yeah, so I can just redraw right here. Here's my lawnmower. I'm applying this force here, 90 newtons. At an angle, if I just draw a horizontal line, this is the horizontal. They say we're 30 degrees below the horizontal. So when I am literally pushing the lawnmower, I'm partially pushing down. That line right there that I've just drawn, I'm changing. And then here, I would have a X component, force applied X, force applied Y. So to divide those two, that's why you use that SOHCAHTOA. This force applied Y is the same as me drawing it here. This board is possessed. So force applied, what the?
It just disappeared. I like your face.
Hold on.
It made a little face.
That was spooky. It'll come back, I think. Okay,
That's
we're,
weird.
that was so weird.
No, the face is gone.
Okay, so back to this. So this force applied, it was blue, right? Applied, Y, is the same as if I were to draw it here. And for some of you, it might be easier to see it if we draw it here. Gosh dang it. There we go. So 30 degrees, this is my angle. Opposite the 30 degrees is Y. So to get FAY, I would do FA times the, since it's opposite, sine of 30. To get FAX, because it's adjacent, it's right next to my angle, I would do force applied times the cosine of my angle, 30. Because FA, the applied force, is my hypotenuse. So, when in doubt, X, cosine. Y, sine, always. And then the last part of this, which, yeah, we have time for. Let me erase all this stuff. How do I find the normal force? Oh, shoot. I have to find the gravitational force and do what with it? Hold on, I gotta selectively erase all this. So if we think normally, we would just find the gravitational force and we'd be done. But here, part of my applied force is downward, so I have to also account for that. So then to calculate, I would do, in the y direction, net force, I'd have normal force, Fn, minus Fg, minus force applied y. Which means, hello Bella, which means the normal force, which we're solving for, is equal to Fg plus Fa sub y. Because this mass times acceleration goes to 0. If I push my lawnmower across the ground, here's me mowing. Is it going to fly up in the air? Gosh, I hope not, unless I've hit a tree stump or something. But if this is 0, I can move these across, and then I can solve by doing Fg, which is just 15 times 10, plus the applied force in the y direction. That's what we just showed with trigonometry, would be force applied times the sine of 30. So 90 sine of 30, which gives me a total normal force of 195 newtons.
Sorry, when you said flying lawnmower, you know the line where the lawnmower?
Yes,
Yeah.
yes. It's a classic.
I learned that it was actually an airplane, like it wasn't an actual one.
Oh, really? I'll have to search into that. All right, so I know that's a lot,
Can we watch that?
if we have time. And then- all right, any more questions about this question? We're not going to go into the bonus parts because we don't want to flex on everyone, but if we wanted to, then all we would be doing is changing up our coefficient of friction. We can solve for that. So, oh, reading quiz? Okay, go back there and I'll give you the password. Okay, we don't have time to do, I do want to just mention one thing on this question. When you're applying forces to an object that's hitting another object, the only thing that adds to our question is contact forces here. So in the same way this would normally just be Fg and Fn, if I push a block into a block, then even though this is the applied force, so my block 1 would be force applied, as it hits this surface, the other block pushes back on it, right? This would be the force of block 2 on 1. And then for block 2, even though it doesn't have an applied force, it has a force of block 1 on 2. And then Fg and Fn. So all this is just Newton's third law. Okay. Anything else on this before we take our last break here? Okay, I showed the other class because we did the to catch a bullet thing, the David Blaine catching a bullet in his mouth. I don't know if I've seen that. But since we didn't do the bullet one yet, instead I'll do this flying lawnmower thing. What do I search? Just flying lawnmower vine?
Yeah.
Oh my god. Hold on, let me rewind it and get the full effect here. Hopefully there's nothing bad. Hold on, let me screen this beforehand. It's only 7 seconds. Wow, incredible. Okay, we're going. Oh, this is not too loud. Is this it, Davia? I've never seen this.
You never seen this?
Oh my god. That was incredible. One more time. Wow, I'm gonna use that every year from now on. Yeah, if you ever forget normal force, just look that video up and it will help you for sure. Wow. All right, I think that's a good stopping point. We'll get cleaned up. We'll do our catch a bullet tomorrow. So train your reaction time tonight.
Alright.
Mr. Henderson,
Yes.
is that all y'all did today? You just went over notes?
Yes, I'm actually, let me stop the recording. Yeah, we went over the practice problems and stuff.